Thousands of extrasolar planets are now known, and although we cannot yet study any of them in great detail individually, we have enough basic data that we can begin to investigate how these planets compare to the planets of our own solar system. This graph from your textbook shows one way in which we can compare planetary properties. In this video, we'll explore how you can interpret the wealth of information that it offers. Let's begin by hiding the images and paintings of selected planets so we can focus on the graph itself. The horizontal axis shows planetary mass, given here in units of Earth masses. That is, a value of 1 represents a planet with the same mass as Earth, a value of 10 represents a planet with 10 times Earth's mass, and so on. The top of the graph has a scale showing the equivalent values in Jupiter masses. The numerical values are much smaller because 1 Jupiter mass is equivalent to about 318 Earth masses. The vertical axis shows planetary radius, given here in units of Earth radii. The right side of the graph shows the equivalent Jupiter radii. Because Jupiter is about 11 times as large in radius as Earth, 1 Jupiter radius is equivalent to about 11 Earth radii. The green dots represent 6 of the planets of our own solar system. For example, this dot represents Earth. Notice that its position is at 1 Earth mass along the horizontal axis and 1 Earth radius along the vertical axis. This dot represents Jupiter, which of course has 1 Jupiter mass and 1 Jupiter radius. The red dots represent a sample of extrasolar planets, for which both mass and radius are known. In most cases, this means a planet was discovered with the transit method, which allows us to determine the planet's radius, and follow-up observations with the Doppler method then gave us the planet's mass. Now consider this question: what are the approximate mass and radius values for the circled planet? The answer is A, as you can see by noting that the planet is at about 100 Earth masses on the horizontal axis and at about 10 Earth radii on the vertical axis. The fact that we know both mass and radius for these planets means that we can calculate their densities. To help you estimate densities, the graph includes 3 dashed curves representing particular densities. This central curve represents the density of water, which is 1 gram per cubic centimeter. In other words, planets like these, whose mass and radius put them on or very close to this curve, all have an average density about equal to that of water. Densities above or left of this curve are lower. For example, planets along this curve have a very low density that is equivalent to that of styrofoam. Densities increase in the opposite direction, so that planets along this curve have an average density as high as that of iron. Now consider this question: what can you say about the density of the circled planet? The answer is B. The planet falls in between the density curves for styrofoam and water, and therefore has a density greater than that of styrofoam, but less than that of water. We can go one step further with the data on this graph. Recall that all planetary systems should form from material that is 98% or more hydrogen and helium, with the remainder in the form of hydrogen compounds, rock, and metal. By using the known properties of these materials, scientists can create models that tell us the expected composition of a planet based solely on its mass, radius, and density. The colored swaths show the models that correspond to different regions of the diagram. For example, this yellow swath represents planets with rock and metal, like the terrestrial planets of our own solar system. That is why Venus and Earth are in this swath. The pink swath represents planets made mostly of hydrogen and helium, like Jupiter and Saturn in our solar system, and the blue swath represents planets rich in hydrogen compounds, like Uranus and Neptune. Most intriguingly, we also see planets that appear different in character from any of the planets of our own solar system. For example, planets in this swath are similar in composition to Jupiter, but with larger radii and higher surface temperatures as a result of being close to their stars, which is why we call them hot Jupiters. Down here, we find planets similar in composition to Earth, but that are more massive. We refer to them as super-Earths. And here, we see planets for which models suggest they are made predominantly of water, either in liquid form or as a high-pressure solid, so we call them water worlds. We now complete the diagram in your book by adding back the artist's paintings of representative worlds. As we've seen, this single graph allows us to say a lot about any planet for which we have measured both mass and radius.